All right, so we're going to be talking a little bit about electrical charge and Coulomb forces. So the unit for electrical charge is the Coulomb, and it's a capital C is the abbreviation. It's quantized, which means that it comes in little packets, and the smallest amount you can have is the charge on an electron, or multiples of that. So it's going to be 1.602 times 10 to the minus 19 coulombs. You will see numbers like it's charged to 5 microcoulombs, it's charged to 4 nanocoulombs, but there's a whole lot of electrons in those charges if you really think about it. And we'll do a little math so that you can see some of that. And also, charge is one of those things that's conserved, which means it can't be created or destroyed. It moves around from object to object, moves around better on conductors than insulators, and it can cancel. So you can have something that's neutral. Doesn't mean that the charges have all been destroyed. It just means there's just as much negative charge as positive charge. So as far as Coulomb forces go, or electrical forces, it is a universal force, which means as far as we understand, it works the same way everywhere in the universe. It is going to act between two or more charges. The math does get more complicated when you add in more charges, and if you're working in 2 or 3 dimensions, you're going to end up working with component forces. It is a field force, which does mean that the two charges don't have to actually touch each other in order to act upon each other. And when we're talking about the two charges, so if the force is between charge 1 and 2, then it's the same force on 1 from 2 as it is from 2 to 1. So back and forth, it's the same. If you do all the calculations and you end up with a negative sign, then the force between the charges is attractive. And if you end up with a positive sign on the force, it is repulsive. You got to be careful doing the math with this also. The attractive and repulsive sign, negative charge, positive charge. Don't get that confused when you're working with negative and positive directions when dealing with vectors and components. So be very, very careful with that. So this is the equation for Coulomb's law, or electrical force. And you would just keep adding on more and more and more of those little kq1, q2 over r12 squareds for each charge that you added into the system. And so this is kind of a basic diagram. You got the two charges, the distance in between the centers of them. Usually they're very, very small charges, so we're dealing with point charges. And then I tend to use Coulomb's constant when I'm working examples, but you can use the permittivity of free space, which is in your book. You'll see that in a lot of the examples. They are just the reciprocal of each other, so either one works. And good math is just good math. So how many electrons are found in a lightning bolt with a charge of 30 coulombs? So if you start off, you know the charge is 30 coulombs, and then the charge on an electron is 1.602 times 10 to the minus 19 coulombs in every electron. To find out how many electrons it is pretty much just a conversion. So you're going to put the coulombs in the numerator, the charge on an electron in the denominator, divide it out, and you get 1.8 times 10 to the 20th electrons. All right, so for this problem, it's a simple Coulomb's law between 2 point charges. And you've got two charges, and the force between them is -3 newtons. And the question is, how far apart are the charges? So I'm using the Coulomb's constant, 8.9 times 10 to the 9th Newton meter squared per Coulomb squared, and instead of the permittivity of free space. And then Coulomb's law. So plug everything in, and we're going to be solving for the distance between the two charges. And so after a little bit of algebra, you're going to get that the square of the distance is something around 0.0061 meters. And then you need to take the square root of that to get your answer. So don't forget that. And you're going to end up with 0.78 meters. So that's the distance between the two charges. All right, next we'll be moving on to more charges and even more charges. All right, so this is a problem where we have three charges arranged in a triangle, and we need to find the force on Q1. So you start off with Coulomb's law equation, but in this instance you have to find the components, Fx and Fy. Fx just has the one component from Q2, but you do have to take into account it's at an angle. So that's where that 4/5 comes from, because that's cosine of theta. And then find the value for Fx. And then Fy, you're going to have two pieces to that, one from Q3 and the other one from the component from Q2. Once again, we're dealing with trig, and you get an answer for Fy. That's not the end of the problem, though. You have to use Pythagorean theorem to put them all back together again, and you end up with your answer for what is the force on Q1.